And so we are recording again. Any questions anyone have on GPS or any of the other things we've discussed? Okay, so we'll pick up there and all right. So the authors have done a lot of work in visual odometry, and so we'll cover this and just trying to balance time in the semester, and so we're going to cover this at kind of a higher level than maybe we did with GPS. It's definitely important, and I can give you a lot of references and information on where you might want to go from here. The Jetson Nanos have, or I'm sorry, the Jetson TX systems have a nice optical flow type demo that's packaged with them. And we've talked about how Tesla is kind of relying on cameras, but there's a little bit of a difference here. This is going to be more of a kind of a computer vision algorithmic type of approach to visual odometry, whereas my understanding of what Tesla is doing is more of just a full-blown, very deep network or networks and neural network type technology. So, all right, so let's look at things here. Visual odometry estimates movement from the flow of stationary objects in a field of view of one or more cameras, right? So here, this diagram showing two cameras positioned slightly differently. And here we can do a little bit of disparity matching. And maybe I'll come back to this after this slide. So with stereo disparity, this is essentially how our eyes work, except our eyes work with, of course, our brain, which is, some far more complex neural network than we've ever implemented in computers. But here we can examine features found in the field of view in both cameras. These features, what are they? Well, they're often found by searching for corners or lines or circles, but typically corners where the pixel intensity varies quickly, right? So we can do essentially a spatial derivative across the scene, and where we see things change a lot, that kind of implies a high contrast, right? And so that might be something interesting. That might be a feature, right? But you can kind of see that, well, it's not easy figuring out what is a feature if all we're looking at is an algorithm examining pixel intensity values, right? So so how do we do that? Well, there's been decades of work in computer vision on finding these features, right? And so if you dive into a toolkit like OpenCV, you'll see techniques of finding these things, right? Now, if a feature occupies very disparate pixels between the two cameras or more, then that implies the feature is close. If a feature occupies similar pixels between the two images, then the feature is far away. Okay, wow. Let's look at these two images here, right? So this is an image from two different cameras mounted spaced apart on a car. And we see here that there's well, let's just look at like this right-hand tail light of that car. And we see it show up in this pixel location. We could count down a number of pixels from the top and a number over from the left and say, okay, now how does that compare over here? Well, it's a little bit different. Maybe it's a little bit more to the right than up here. And maybe it's kind of hard to tell, but maybe it's the same height. But that there's some difference. Now let's compare that to this truck way out there. Well, there's some difference there too, but maybe it's a little bit less. Let's compare like this line here. Well, that's looking even more different. How about this line? That's showing up in very different locations here, but out here farther away, what we perceive as farther away, maybe it's not so different, right? So that's the idea, is that the way these imagers are set up, features that we can identify, right? So if we did a spatial derivative on this image, these little white lights would show up as a big rate of change. Maybe these black tires would show up also as features. All these things could be features that we would pick up and try to analyze. And but you know, one way or another, we're kind of doing this triangulation process. We're looking at how disparate are these, you know, particular features between the pixel locations in these two images. Things that are roughly in the same location can be perceived as farther away, whereas if they're you know, very disparate, that's implying that they're very close, right? And then we so we got some idea of distance, and now we can do this feature detection. We try to choose some objects. Now in this case, you know, we're trying to determine how far our ego vehicle is moving, right? So we probably don't want to pick something else that's moving, right? This car, this truck, well, it's moving too, right? So somehow we need to discern that and really maybe work with fixed features like these poles right here, or these lane markings and stuff, right? So somehow we pick up what is a feature, and then we try to throw away things that are transient in that image or moving, and try to settle on things that are fixed, right? And then we take our previous map, okay, of things, right? So this actually doesn't match this picture. I don't know why they chose it. You got some pedestrians here and that type of thing. But the idea is that you've got some previous frame that you've stored, and now you try to match features between this disparity map, and once you process these two images, you're going to have a disparity map here. You try to pick out the same features, right, and match those features, right? And then you can look and see how those features moved from one image to another, and ultimately discern motion, right? And then if you know your initial position and you've calculated some motion, then you can use that to update your vehicle position, right? So so this first step was doing this stereo disparity, or that triangulation. And so what we've done basically in that step is map our 2D features to some three-dimensional representation, right? Where now we have a little bit of depth information in it. Then we match our features from one frame to another. We might take a little local window and slide it around where we compare the previous frame with this frame, and we look to where that provides kind of the minimum sum of the absolute differences, right? What is that? So it's kind of like a root mean square type of error that we're pretty used to dealing with in electrical engineering. But what do we have here? We take the difference in the pixel values, take a difference, but we don't really care whether that's a plus or minus difference, right? So let's take the absolute value of it. Now, for each of those pixel locations in that window, let's sum them up, right? And we slide that window around until that whole sum is a minimum, right? And then that means that our features are matching, right, between frame to frame. But we may have offset it in X and offset it in Y, right? So that's what that sliding window is doing, right? So then we can record that X and Y difference, and that shows how much we've moved in from that one frame to another, how much that feature has moved, right? So now we do want to kind of ignore other moving objects. We also want to make sure that we're really matching up the right feature, right? So if we go back and look at this, ooh, you know, that feature looks like, you know, that left tail light looks like that right tail light, that left tire, rear tire looks like that left front tire, looks like the right rear tire. We got to make sure we're matching these things up correctly, right? But especially we want to make sure we kind of ignore something that's just moving through the frame momentarily, right? So what we do is we kind of look for that largest set of self-consistent matches, right? So we want to take all, you know, a bunch of different features. We want to do this for all these different features, and then we want to kind of imply some motion associated with that, and then make sure that that's all self-consistent, right? So we shouldn't have, let's say, this, you know, far end of this lane stripe moving in one, you know, distance and direction, and the other end some other way, right? So it's a physical object, you know, some thickness of paint, and it should be considered a rigid body, right? And it shouldn't be being torn apart, and so it should be, you know, produce a self-consistent set of matching. Then so once we're happy with that, we can calculate that frame-to-frame motion. And still, you know, still a lot of chances for errors, and so we take that frame-to-frame motion, apply it to the last frame, and project it backwards, right? And then we look for, oh, how does it match to that previous one, right? So, and then we can optionally try to use some of that depth information from that stereo processing to improve the matching. So ultimately, we're going to use the calculated motion of those features to infer the pose, or the location and orientation of the ego vehicle, right? And this still requires an initial position to estimate. But we can build up a full trajectory frame by frame, right? So what are some of the challenges with this, right? So if we're trying to figure out how far we're moving along a road, Well, if we've got other cars out there that are moving, that's going to be confusing. Bicyclists, pedestrians, whatever it's moving, even swaying trees, right? As the book kind of mentions that. You need to deal with occlusions, right? So what if you're monitoring a feature, but then it gets covered up by something in the next frame, right? So now you're not able to find that feature, right? So you've got to, your algorithm needs to be robust to handle some momentary or permanent occlusions, right? So you might have a feature drop out of a frame and then come back in the next frame because it was occluded, maybe by a passing truck or a sign covered up whatever you're tracking or something like that, right? We got to find the features to begin with, and that's a non-trivial process, right? We can kind of slip out of synchronization and kind of lose track of our features if we have a high rate of change, like we're turning around a sharp corner and we're unable to match those features, particularly as we're turning. There's now some kind of trigonometry involved and so some nonlinear things going on there. So if we only have one camera, it's a monocular system. We need to use scale of the size of things in order to infer distance, right? So an example, we know that stop signs are, certain size normally. Sometimes they're bigger, sometimes they're smaller, but normally they're consistent size. And certainly once we've picked it up, let's say somehow we've got the super feature detection that isolates a stop sign. Not really how it works, but let's just assume that, right? So as we're tracking that, as we're approaching it, it's going to get larger and larger. And so we can infer from how many pixels it's covering up or occupying in our image, and infer from that how fast we're closing on it. So yeah, book goes into a lot more details than this, but again, we're just trying to make some trade-offs on what to cover in the course. All right, so any questions real quick on that? Okay. Not hearing or seeing any questions, so let's jump on to kind of the second half. This is maybe the third half of localization. Will probably fall into a third lecture eventually here to finish this up. But now we've talked about localization using GPS, odometry, and this visual odometry, right? Dead reckoning, whatever you want to call it, right? So there's some other techniques too that we'll touch on. We want to be able to have a reliable and accurate localization system, and sometimes one single sensor isn't going to do that, right? So we're going to talk about fusing multiple sensors together with a Coleman filter initially, and then we'll talk about a particle filter, and then SLAM, which is simultaneous location and mapping. Particle filter is going to require you to have a map already that you can match yourself to and try to figure out where you are in that match by comparing what you would expect to get given that map and a particular location from comparing that to what you're actually getting, right? And then, but sometimes you don't have a map, and so we could build one up as we go. We can kind of hunt around and do the simultaneous location and mapping approach. All right, so As I said, no sensor is perfect. As we talked about, IMUs drift. GPS is useless in tunnels. Visual odometry struggles with various impairments. So can we combine these to get the best of the combination? All right. So we might be interested in greater accuracy or greater availability, right? What do I mean by availability? Well, for example, GPS is available when we can see the sky, but if we're in a basement or a tunnel or a cave, then it, or subway or something, it's not available, right? So availability is the amount of time, the fraction of time that your sensor is actually providing accurate information, right? So Coleman filter is a classic and in certain cases optimal way of fusing data. We're gonna dive into this a little bit here. So multiple sensors may be combined for situations where, for example, GPS is not available. Here, the IMU, in this case, that's that inertial measurement unit that has accelerometers in it, gyroscopes, and magnetic magnetometer. We can sample this thing many times a second, 200 kilohertz, 200 kilosamples per second if we want, right? So pretty fast. These things might be connected over an I2C bus on your microprocessor bus, right? So we can get very fast update positioning, but it drifts, right? So the GPS, typical older consumer grade GPS's output 1 fix per second. You can spend a little bit more on a newer system and you might get 10 fixes per second or 10 hertz update rate. But that's about it, right? So, but we can use a Coleman filter in order to kind of extract out the best of both worlds. And this is a recursive type of filter where we have a prediction step and where we're taking the data from this IMU and kind of predicting what our new position is based upon the accelerations and rotations and whatnot that we perceive from this. And we update our pose or location and orientation. But then we might want to update that or correct it for any drift using our GPS. And so it's kind of iterative process. So that all sounds good. Can we do this in an optimal way? Well, let's back up a bit and talk about the big picture. What are we trying to do? We're trying to estimate some state. And actually, Kalman filters are fairly generic. They're very, very common in robotics, but they're used in tracking algorithms. If you've got a radar or a sonar that's tracking an object, then you might use it. You might use a Kalman filter in that application also, control systems in general. So let us consider the state of a vehicle or robot as its pose, right? So that might be XYZ location or latitude, longitude, and altitude, and then an orientation, right? A pitch, roll, yaw, or something like that relative to some origin orientation system. It is not likely perfectly predictable nor perfectly observable, right? What do we mean by that? Well, so we have this vehicle or robot. Let's say we've instructed it somehow, either autonomously or remote controlled, or I just pressed on the accelerator and turned the steering wheel, and I've asked that vehicle to move a certain distance at a certain angle for a certain period of time, right? So we can pretty well predict where we ended up at. but we just talked about some error sources and all of that, right? So it's not perfectly predictable, nor is it always perfectly observable, right? We have noisy motions and we have noisy sensor readings, right? So again, we're thinking this is vehicle or robots, but boy, this is very generalizable, right? A system that is not perfectly predictable nor perfectly observable. So there's some random, we can describe these as random variables, maybe following some probability distribution function. So we want to estimate the state X of a system given prior observations Z and inputs U. And I've tried to kind of keep my notation straight, but I've pulled this from a lot of different resources. And so you might see some slippage of or swapping of notation. Sometimes this T is noted as K, since they're typically in discrete steps. Yeah, so here what we're saying is there's a probability that xt is a certain value given prior observations of where it was at and certain inputs, right? From, let's say, the beginning of time, time one, up to t, right? So this is its history, and this is our current estimate. And we're recognizing that these are probability random variables. So there's some probability associated with this, right? So that was state estimation. Now I'm going to take it a little bit farther. And, we could spend an hour deriving this. I'm not going to, but again, if this is interesting to you and ends up being part of your project or research, you certainly dive into this. But we're going to use Bayes' rule, right? So if you remember from your probability and statistics course, you hopefully studied Bayes' rule, and that's helps you transform conditional probabilities, where if you're going to say, what's the probability of X given Y, and you want to kind of flip that around and examine the probability of Y given X, well, you do that through Bayes' rule, right? And then there's this Markov assumption. Well, this gets applied a couple of times in deriving this general theory for recursive state estimation. What does Markov assumption? I'm guessing you didn't. I'm hoping you studied Bayes' rule in your probability and statistics course, but I'm guessing that you did not run across Markov assumption. That tends to be more graduate level type thing. The Markov assumption means that if I'm, let's say, traveling through, let's see, can I get, oh, I can't draw on that, can I? What if does that show up? Yeah. So what if I'm traveling along here and I have this history, and now I want to know where I'm at right now. Well, if I know the prior, it doesn't really matter how I get there. In many cases, not all, but in many cases, right? I might have come up there from this direction, right? If I just want to know this based upon this and maybe this transition, right? I don't really care how I got there. That's essentially the Markov assumption or approximation, right? So we're going to assume that these are Markov systems and that we don't really care about time, yesterday. We only care about what just happened and all. So then there's total probability theory, and then the independence assumption. So I'm just kind of stating these in case you wanted to dive a little bit deeper on it. But this last independence assumption here is saying that what we know about the future, perhaps we know something about a future state, it doesn't affect what we believe about the past, right? So it may seem obvious, but it's still an assumption that we're making, and it doesn't always hold, right? But given these are pretty broad assumptions. They apply in a lot of cases, right? Well, Bayes' rule is absolute, right? If you do it properly, that's absolute. Total probability theorem, that's absolute. These others are assumptions, and they generally hold in a lot of interesting cases, right? So now we want to estimate our current position based upon a belief of where we were before, t minus 1, an update due to a system input, and an observation of where we are, right? Okay, and all of these are uncertain. If this observation was certain, we wouldn't care about these, right? We just say, where are we? Oh, that's exactly where we are. Well, no, we can't. This is has some level of uncertainty. Where we were before, well, we have a belief, but that there's some uncertainty associated with that too, right? And then we have some update, but maybe the system didn't move in exactly or behave in exactly the way we instructed it to, right? Maybe there was a slippage or something like that, right? So, so that's what we want. So all of that leads us to this, right? Let's see. Can I get my so now we have this belief of, in here, I'm sorry, I switched to K's, but these are equivalent to your T's. But again, sometimes K is used to emphasize that this is often done in a discrete time approach, right? So we've got this recursive relationship here where we have K is x of k, or belief in where we are at time k, step k, is a function of these times before, steps before. So this is our observation model, right? Where the z is our observation conditioned upon where we actually are, right? And then this is our motion model, right? So given where we were and some system input, then we'll have some probability that we'll be at this x of k location, right? So this is our motion, and it's a probability. This is our observation. It's also a probability, right? So now this we can see is our prediction step, right? So now we have this prior belief of where we were, right? There's some level of certainty, but that's our belief of where we were. And now we're going to step that, and then we're integrating this, right? So we're considering all these different potential beliefs and stuff, right? So and then these are weighted by these or updated by this correction step, right? And this eta here is a scale factor that comes from our initial application of Bayes' rule to normalize things so that these are true probabilities, right? So if you integrate the PDF, it comes to one, probability of one, right? So now this overall is a general statement, right? General equation, but there's a lot to kind of pick apart here, right? What are these probability distributions, right? So these are very generic at this point, right? So these probabilities. What are these models? What help us kind of move and all? So to implement this in real life, we'll make some assumptions, right? And then, so this is like the general, what we call the Bayes filter for recursive state estimation. But typically, to actually make use of this, we've got to make some simplifying assumptions. So the Coleman filter is a very popular one and common one, right? So, but this has some pretty strong assumptions that are associated with it, right? Sensor and motion probabilities can be described by Gaussian distributions. Basically, every random variable that's present in the system needs to be a Gaussian distribution. All right, and then also our prediction and observation models are linear. Right, so this model here of given the true x, how do we sense that observation model, that's linear process, and that this motion here is a linear process also, right? Okay, so big assumptions there, but when those hold, now the Kalman filter recursively predicts a motion and then updates it based upon a measurement, right? So, and this can be used for control and also sensor fusion. So it's used in a wide variety of different ways. So how much to weight the prediction versus the update is determined by the Kalman gain, right? So if we have some uncertainty about this prediction, right, is how do we take those inputs and then predict our current state, right? Prior state, some inputs, current state, right? So there's some uncertainty associated with that. Again, could be a wheel slip, could be an inaccurate or imprecise steering input, something like that, right? Or some current that's pushed us off or whatever, right? Now we also have this measurement. Now that measurement is going to have some uncertainties also. How much do we trust this prediction versus how much do we trust this measurement? Really, what we want is a weighted kind of average of these two, and that is going to be done by this Kalman gain, right? So now the question is, do we just kind of pick a number and hope that works and try it, or is there a way that we can figure that out exactly? Well, yes. The Kalman gain is actually calculated from the covariance. So what we're going to do is we're going to estimate our variances in the system, right? So, and covariance is kind of relating different variables to each other and their variances, right? So, but ultimately, how much do you trust the prediction? How much can you trust the observation, right? So we want a weighted sum using the variances, the prediction, and observation to update the mean, right? So the mean is going to be our best guess at what our state is, right? So we're trying to estimate the state. All right, here we go, some equations, right? So here we're going to have all these different variables, and they're each going to be have some coefficients in front of them, which may be matrices or vectors or matrices, depending upon the number of dimensions that we're working in, right? And and these might scale from sensor values to real world values or something like that, right? So so this is our motion model, where this WK here is noise, right? And then it's being scaled by some value, and we can assume that that's a unity matrix or something like that. But yeah, so and it's got some inputs UK that are driving the system, and then we have this existing state. But then that gets transformed to the next state, right? And then we have this observation model here, right? So now we have this actual position or state, and now we're going to measure that using this h prime of k, and that's kind of your sensor transform function, along with the sensor noise, right? So, and that's going to produce our estimate or observation of where we're at, right? So now, x sub 0 has mean of this x tilde is 0, and covariance of a sigma 0. Sometimes this is referred to as, oh, it didn't show up, capital P. So sometimes some notation uses this capital sigma, and some uses a capital P. And these WK and VK here are zero mean Gaussian random variables. And this is just kind of a fancy way of saying that between this one sample of noise of the motion model and a noise of the sensor model and another sample of those at L, and the expected value of this product of these here is going to be what this is really telling us is that these W's and V's are independent of each other, right? And that's showing up in this Q and this R and these zeros up here, right? And so that W is independent from V. And then this delta, this is a Kronecker delta. So this is equal to 1 if K is equal to L, and it's equal to 0 otherwise, right? So only when these K's and L's are the same do we have a value here. Otherwise, it's 0. So this is talking about autocorrelation. If you studied this from your probability theory course, so this is saying that there's a autocorrelation, but not really cross-correlation. So again, in words, this WK and VK are independent of each other and independent one time to the next, right? With even like WK is independent from WL and VK is independent from VL, right? So now we're going to go from this kind of truth here to estimating, right? So hats now are going to represent our estimated values here. So now we're going to have this kind of expected value of, given all that we know about measurements, this is cap Z here, of all our prior measurements, and this X of XK. So this gives us a estimated position given the prior, right? And now this is our covariance, and so now we can look at taking our true value and subtracting out our estimated value, and then doing multiplying that by the transpose and taking the estimated value of that is going to give us our covariance, right? So a lot of math here. Then now we're going to take these same equations here, but now we're dealing with these estimated values, right? So here we have this x of k, our prior time position estimate, given all of our prior estimates, right? So it looks a little weird because they're both k minus ones, but this is all of our condition prior estimates, and there's some function that updates that along with some inputs, right? And we're not carrying along the noise anymore because we are dealing with estimated values, right? So there's an expectation implied here, right? So now so this is predicting where we should end up at, right? And now we want to update that. So we're taking our sensor reading and we're subtracting this kind of scaled version of where we actually think we are, right? And so this is where we think we've measured. This is where we think we are, and this h is just transforming the units to be the same scale. And then we're multiplying it by this capital K sub k. This is called Kalman gain, right? So this is kind of weighting our measure versus update or prediction, measured versus prediction, right? And then we add that to our prior location, and that ends up with our next estimate, right? So how are we doing on time here? So let me draw something out for you here now. So draw on the right screen here. So let's take this example I've seen is like looking at a ship moving in a harbor, right? And we've got a radar tracking it, right? And so this is maybe x sub 1 given 1. And then this is 2, 2. This is 3, 3. This is 4, 4. And now this is going to be the vector that has updated us, right? So and then so this might be let's see, 5 and 4, okay, and then we might measure it over here, right? So this is where we predicted it. This is where our radar measured it. And now we can look at this vector here that is representing the difference between our predicted step and our update step. So what we want to do is, or actually our measured step, right? And now what we want to do is figure out how much do we trust the measurement versus the model that updates it. And maybe the real location is right there, right? Maybe the real location is right there, right? So we're going to kind of figure out how much to emphasize this versus that using this. Okay, so so here's the way we do this. sorry, let me get my laser pointer back again. So yeah, we're going to use this sigma k condition on k minus 1 as the covariance matrix, right? So how do we find that? All right, so, well, again, we're going to iteratively do this, right? So we're iteratively doing this predict and update and that type of thing. But this Kalman gain here is this function of how much noise or variance do we have in this system. And so how do we come up with that, right? So we do it iteratively, right? So we're estimating the amount of variation we have in the system. So and so we can take the prior information or prior estimate and again transforming it using this transformation there, and using our estimate of our Kalman gain, and then updating it based upon our measurements, right? So, and this is the amount of noise we have in our measurements. So, all right. There's a lot to unpack there. I know. I just if you're a math-oriented person, I think this is fascinating the way it's developed here. But just the main thing is that we're doing a prediction, we're doing an update. All these coefficients that you see here are weighting or transformation factors, right? So sometimes they just might be unity or just translating an input to how much effect that has on your position, right? If you had a certain angle of or force on your accelerator pedal, how does that transform into a motion, right? So so that it gets messy, but it's handy to keep these along so that we can plug in values for them ultimately, right? So all right, so now what about this Kalman factor? It turns out that it's optimum when its conditions are met, and that's why it's so universally used. It can be used for navigation of a robot or drone, where the inputs are the control inputs to the propulsion system, and then updated using pose measurements, right? So we can measure, we can have these inputs and control inputs, and then measurement, and now we can kind of continually optimize our navigation, right? We might find that, oh, we've put in too much steering input and we need to back that off, right? So that can automatically be done in an optimal way. It's also used in sensor fusion, which is really what motivated our talk here, our treatment of it here, right? So here, the inputs to the prediction step are these noisy sensors, but are refined using possibly slower or less available, but more accurate sensors, right? So kind of a navigation type thing or a sensor fusion type of thing. So here's a little bit more involved treatment of it from your book. Again, here we have this these high update rate, nearly always available type systems, sensors, but they are susceptible to a lot of drift, a lot of errors, that type of thing, right? So, but we can use these to predict or propagate through where we think our next position is, right? We can make some readings. We can translate what a particular value coming out of this chip means, or set of values, this 9 degree of freedom type of data. You take all those, run it through some model or some big matrix, right? And that will give us an output that is where we think we are, right? But now we can fuse that with some GPS or maybe some analysis related to a map and matching up what we're seeing with what we're perceiving around us to what the map tells us should be, right? So we're kind of registering ourselves on a map. So all this can be more of our more difficult to calculate very fast type of things, but it can be used to kind of correct the drift and errors associated with these other type of things. And ultimately we get a better, a superior value for our pose. All right, so recall that the Coleman filter needs Gaussian random variables, basically everywhere. And kind of the interesting thing here is a Gaussian random variable transformed by a linear function is still Gaussian. But if any of these functions are nonlinear, then that random variable at the output of the function is no longer Gaussian, right? I'm going to show this horribly crude example in a minute. So nonlinear functions often arise when working with angles, right? So some LiDAR, definitely radar, because we're tending to work with bearings and angles and that type of thing. Trig functions are nonlinear, right? So let's take a look at this, right? So here's a linear process. We got a straight line. This is our transform, right? And this might be our model, right? That says, okay, if we have a certain input, then our that's going to result in an output, and if it's it's always going to be scaled by this straight line, right? In this case, it's got a negative slope and some positive offset y-intercept, but it's a linear transformation. So we can map this point up to here and over to there, right? And this point up to here and over there. This point, which, yeah, that's its mean, right? And so this is its old mean or prior mean. And then that gets mapped over to here, right? So it's basically what we've done is we've transformed that mean, right? And then we can, project these points, all these points gets projected off of this line, this transformation out to this new value. But you see, this is still a Gaussian, right? Trust me. I know my drawing is terrible, but we're translating the mean and variance. So this n is the shortcut for a normal distribution, right? So we've got now in terms of y as a variable instead of x, but we've taken that original mean and we scaled it by a factor of a, and added an offset to it, b, right? And we've scaled the variance by a squared, right? But it's still a normal process. We just need to update, right? So if we're going through this Kalman filtering process, we're just updating the mean and the variance through that, right? So well, what happens if you have a nonlinear process, right? So this is no longer a straight line. It's, some horribly nonlinear process, right? So now let's project point by point, right? And I don't even know if these match up, but you can project all these, and what you'll see is that this thing is not going to look like a Gaussian anymore. What does the mean? Well, you could numerically calculate a mean, and you could, do something, right? But means and variances are just kind of those first order moments of describing a parameterized probability distribution function or density function, right? So there's an equation implied behind those, right? If we calculate the mean of or variance of a uniform distribution or a Gaussian distribution or something like that, there's that's a parameter, but there's some equation or model behind that, right? Here we end up with this garbage, right? It's not garbage. Maybe its mother likes it, but what does the mean or variance even mean in something like this, right? So it doesn't. So what do we do? Is all hope lost? Well, let's consider if we have a weakly nonlinear process, how do we linearize these things, right? In a local area, maybe around the mean, right? So hopefully you've learned Taylor series expansion around point A, right? This is one of kind of your most fundamental engineering approximations we make, right? So here, this, in general form, we can approximate our nonlinear function as a, evaluate that function at a particular point A, but then add to it this derivative at A times x minus A divided by 1 factorial. And then add to that the second derivative at A divided by 2 factorial, and then x minus A quantity squared, and so on, right? Dot, 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 out to infinity. If you take that Taylor series expansion out to infinity, then yes, that will accurately describe f of x. The fewer terms you include, instead of infinity, you're including fewer terms. Okay, I got 14 minutes. Then the narrower range over which around A that this thing's going to be valid, right? So it's still going to be a pretty good approximation if you have a bunch of terms, but the fewer terms you have, the less perfect that expansion is going to be around that point A, right? So we want to get to a linear approximation, right? So this turns out as a coefficient. That's equivalent to our B in our classic y is equal to ax plus b type of equation of a straight line, which is a linear system, right? So, and this is equivalent to our x term, right? So this is our slope of our line, and that's our intercept of our line. So if we included a square term, now we've got a kind of parabola type of thing. So no. We are going to truncate our expansion right here, right? So now, as it turns out, this is all fine and dandy if we're in one dimension, but typically we're working in greater than 2 dimensions, well, normally 2 or 3. If you live in a 5th dimension world, yeah, I want to talk to you. But here, 2 or 3 dimensions, now we need to use a Jacobian for the derivative. What's that Jacobian? Well, this is that, partial derivative in a matrix that's doing all that stuff, right? So instead of just a single dimension derivative, right? So let's consider a millimeter wave radar measurement. So when we do a radar measurement, it doesn't have to be millimeter wave, but that's the band we tend to use in autonomous vehicles. So now we have, as our measurement tuple, we've got a rho, which is our range to the distance, right? Some meters, kilometers, or feet, or something like that, right? And we got this phi, which is our bearing, right? And then hopefully we've got a rate of change, right? So if we have a Doppler, I should have maybe added in a millimeter wave Doppler radar measurement, then we can perceive how fast that object is moving relative to us. We call that the range rate in radar, right? So we've got three different variables here that we're measuring. And now we can take these partial derivatives of the range with respect to the position in x, y, and velocity in x and y, and then so on with these others, right? So, and now the prediction step is the same. The nonlinearity in this case is arising in our measurement, right? Because we're using this radar and it's sweeping around 360 degrees and it's taking a range at every some number of degrees or millidegrees or something like that, right? And so that's where the nonlinearity is arising. It's arising in the measurement. So in this case, the prediction step, that's our motion model. That's still linear, so that's cool, right? But here we're going to say that our now our y value is our measurement with this predicted value, where now h is this function that maps Cartesian type coordinates to the polar coordinates, right? So so that just is putting us in the right coordinate systems. So, but we see that this transform is highly nonlinear, right? All right, so then our update state here, I'm just going to kind of present these, and then we'll move on quickly here. But sorry, we've got this S here is our total error. We've got this Jacobian matrix, our covariance, estimated covariance matrix, and R is our measurement noise. And so then we can calculate our Coleman gain in same way, and where we're scaling this covariance, estimated covariance matrix with the amount of noise in our system and or errors in our system, and this Jacobian there. So, all right. So that yeah. Again, I'm kind of zipping through some of these equations here, but just the point you want to take away from this extended Kalman filter is that we're doing this because we got a nonlinearity. We linearize it around a specific point. And so it's an approximation. And as long as we're kind of weakly nonlinear, then we can kind of get away with this Taylor series expansion. There's actually more generic forms called a Volterra series that deals with a little bit stronger nonlinearities, but even that is still assuming it's somewhat weak, right? And then we we're expanding that around the point, and we're linearizing it, right? So now we can transform that mean through that system and still try to keep up with things, right? But we're really just dealing with one point if we do that, right? It's just that mean, right around where A is, right? And that seems a little bit sketchy, right? So to use a highly technical term. So there's an improvement on that called the unscented Coleman filter. Rumor has it that they called it unscented because they felt like the extended Coleman filter kind of stunk. I don't know if that's an urban legend though. The unscented Coleman filter improves on the extended Coleman filter by propagating the Gaussian random variable through multiple points of the nonlinear model instead of just the mean or that A, right? So still requires nonlinear to be quote unquote mild and the random variables to be Gaussian. Okay. So next week we'll pick up here and talk about what if these conditions do not hold, and that's basically going to go to a numerical model using Monte Carlo techniques, which is basically running lots and lots of experiments with lots and lots of different points. Okay, and so we'll look at that. There's a link, and if you click through on a particular week on Moodle, right? If you click on that link, no, I don't. Then you'll see that I think on this week's link, you'll find a video that explains a particle filter in one dimension with no equations. It's kind of a cute thing. Pops up on your first search like it's the highest Google rank thing and on YouTube for explaining a particle filter type of thing. So, but it's linked there. And so it would be helpful if you looked at that beforehand. I did. So I understand we've got a lot going on. I was not sure if I wanted to give an assignment, but I did have it planned. So let's toss it out there. And really, it's let's use your judgment on how fast you turn this in, right? So, but for those that are in the graduate course, I'd like you to code a Kalman filter in a language of your choice. Now, you're going to find lots of examples and stuff. So sure, grab those examples, but put it together and come up with your own code. There's a lot of already pre-built Kalman filters and SciPy, NumPy. There's a Python package you can, I think you can pip install this called PyCalman. If you're not a Python person, you want to work in MATLAB, or I'm sure actually there was a C++ one that I saw. So basically, there's going to be some functions out there that you can just call, right? So if you're in the undergraduate course, just look at this and then create a test and an evaluation. If you're undergrad, do it in 1D. If you're a graduate program course, then do it in 2 or 3 dimensions and plot your results in some way. Create your own data. You're going to want to add some noise in that data, maybe have a ground truth with no noise, but also have some data that has noise in it, measurement noise, update noise. So we can talk about this. I set it out for a week, but maybe in reality, you continue to prioritize your project abstract and initial research report. I'm just, so we can talk about this next week a little bit more, but if you're good to go, wanted to get this assignment out to you so you can jump on it. So, yeah, that's it. Any quick questions? Okay, so go to Moodle, download your feedback files. That's a problem. I don't really know exactly how Moodle works on the student side of things. So, but they, I've uploaded feedback on your projects, and then I'll start looking at your research reports this week. And so again, due dates are for your convenience. Just don't get behind. Also, on the GPS assignment, I can, someone did ask if there's a different way to do the assignment, and I can provide some alternatives if you want to do more of a thing. I'm still thinking about a appropriate one for that, but you don't have to use yarn. You don't have to use, just use string or a wire or whatever, or use a straight edge ruler or something like that. It's just kind of go through that exercise and just get a feel for how multilateration works. All right, so that's it. I'll see you next week. All right, Alpha Cyrus.
Thank you, Professor.